Welcome everyone. So, to, Today we will be discussing about another live session of this course called Chemical Crystallography. So, the professor of this course The professor of this course is Professor Anshuman Royjyoti from ISM Mohali. So this course has started on 25th of July, and currently now we are in the seventh week of this course. So every week, in this Google Meet link, so we are meeting, and before proceeding, I want to say that since we are kind of in the middle of this course. So if you have any questions, so you can post your questions in this ask a question tab. If you are having trouble from any part, you can take the screenshot or write about the time of that video where you are having the problem, and you can post your question in this ask a question tab in this SWAM portal. Okay, so we are in the week 7, and this is the live session number 7 of this course. And today we will be discussing about assignment 5. So this assignment 5 was due on 31st of August, that is 10 days earlier. So I hope all of you have submitted this assignment. So today we will be discussing about the question answers of this assignment and the related content from week 5 of that 12 week course. Okay. So the first question was that the PXRD, so this was a true false question. Okay. And the question was that you have to state whether this statement is true or false, that the PXRD pattern is more spread out when we use copper radiation instead of molybdenum radiation. So uh, you have to know that for in case of copper, the K alpha radiation which is used, so what is the wavelength for that? Okay, so for copper it is what it is 1.54 angstrom, right? So when we are talking about copper here, so the wavelength is 1.54 angstrom, and using that we can achieve a maximum resolution of 0.77 angstrom. So I hope you know how to do that, right? So this is obtained from the Bragg's law. So Bragg's law is a very basic, a very universal concept which is applied in many places to solve questions. Okay, so what is Bragg's law? Bragg's law gives us that 2D HKL, I'm not writing, 2D sine theta equal to n lambda. For first order reflection, we can take n as equal to 1, so we will have this Bragg's law. Okay, now when we are using this copper, okay, so when we are using copper, then this lambda will be equal to 1.54. Now suppose we want to achieve the maximum resolution. Okay, then what we will put? We will put sine theta equals to 1. Then if this part becomes 1, then we will have d max is equal to 1.54 divided by 2, which will come out to 0.77 angstrom. Okay, so for K alpha radiation, the maximum resolution will be 0.77 angstrom. However, if we go to molybdenum, then for molybdenum also it will be like alpha of molybdenum divided by 2. So that is for molybdenum the K alpha is 0.77, right? So this will come out to be 0.35. So then we can see that using molybdenum we can achieve a very high resolution, higher resolution. Okay, so that is why researchers kind of prefer to use molybdenum radiation while taking the single crystal XRD data, and also for the powder XRD diffraction also. However, so let us now understand that what radiation should we use, because there is a definite choice of radiation for different purposes. Now this is a normal PXRD pattern. So this is actually the PXRD pattern of benzoic acid, right? So you know what is benzoic acid? So we have a benzene ring simply, and then we have a carbon. So this is a simple organic molecule. We can get its crystals very easily. And so this is benzoic acid. So this is the carbon double bond. Yeah. So here when we look at the PXRT pattern, so it is taken from 5 to 50 degrees. Okay, now we will not focus on the full pattern. Let us like focus on these major portions here. Okay, so this is like my first peak, right, which is coming at, so if this is 10, then this should be 8. Okay, so the first peak is coming at 8 degrees, and then if we go like 1 2 3, I'm not writing all of it. So this is my 12th peak, which is coming at 30 degrees. Okay, so this is my 12th peak, which is coming at 30 degrees. Now what we will do, we will again apply Bragg's law here. Okay, so you know Bragg's law. So what we will do is we will like divide. So what I'm trying to say is, suppose at first we have taken copper, right? So if we have taken copper, we will write 2d sine theta when we are taking copper is equal to some lambda. Now if we take moly, then that form, now this d, what is d? D is basically the interplanar distance, right? So you will understand that suppose if we are having the same molecule, if we are having the same crystal structure, that is benzoic acid in our case, then if we talk of any particular plane, like suppose 100 or 111, then the interplanar distance which is used in the Bragg's law, that will that has to be independent of whether we are using copper radiation or moly radiation, right? So the interplanar distance is something which is independent of them. Hence the DH scale will be same in both the cases, right? Sorry. So here also the D will be the same, but we will write sine theta moly equal to the wavelength used for moly. This will be the wavelength used for copper. And then what we will do, we will take the ratio of these two. Okay, so this it is a very common practice to do this in mathematics, right? So we will take the ratio. Save it. Now if we take the ratio, we will from here, so if we take the ratio, we will arrive here. Okay, so this wavelength of copper divided by the wavelength of molybdenum will give me this, what will happen, this 2 and 2 will cancel out, this d interplanar distances are written here, then sine theta of copper divided by sine theta of moly. Okay, now what we will do, we will put the values of the wavelengths of copper and molybdenum, right? And this is 1.54, for molybdenum is 0.17, and this DH scale, since the interplanar spacing will be the same, then these two will cancel. So if these two cancel out, then we will arrive here. Now what we will do, this excuse me, Okay. So we were here, right? So this PXRD pattern, so you can see here that this was taken using this wavelength 1.54. So 1.54 means this is the wavelength of copper. So this PXRD pattern was taken with copper K alpha radiation. Okay, and using copper K alpha radiation, we got the first peak at 8 degrees. Okay, but here you should remember that when we are plotting the PXRD pattern, we are plotting intensity versus something which is called as 2 theta. Okay, so this is 2 theta. 2 theta. So if 2 theta is 8 degrees, then for the first peak, we are now focusing on the first peak. So for the first peak, my theta will be 4 degrees, right? So if we rewrite this equation, then what will happen? This means this will be equal to 8 degrees divided by 2, that is 4 divided by sine theta for MO. Then what will become a sine theta of MO? So this into this is equal to this into this. So sine theta for molybdenum will be this 4.0 degrees into 0.71 divided by 1.54, which will come out to be 1.84. Then the 2 theta, because for PXRD pattern we need to plot the intensity versus 2 theta in the x-axis, right? So the 2 theta will be 3.6 degrees. So you can see that this peak, which was coming at 8 degrees when we are using copper, will now come at 3.6 degrees when we are using the molybdenum radiation. Okay, now let us talk about this 12th peak, which was coming at 30 degrees. Then half of that will be coming at 50 degrees, and the sine theta molybdenum for the 12th peak. So this is for the first peak. Okay, this is for the first peak, this is for the twelfth peak. Okay, the sine theta is coming out as 6.9, and then my 2 theta in molybdenum will come out to be 13.8. So you can understand, right? The thing which was coming at 8 will now come at 3.6, and the 12th peak which was coming at 30 degrees will now come at 13 degrees, 13.8. So what will the PXRD pattern look like? The PXRD pattern will actually look somewhat like this. What will happen? All the peaks will come very close to each other, and then the problem is then it will be actually difficult to distinguish between the peaks when we are trying to suppose compare the PXRD pattern of one polymorph with the other. Okay, if we need peaks which are spread out, right, so that it is easier to visualize, easy to compare. So that is why when we are using radiations for different purposes, we have to keep in mind that what we want to analyze and accordingly choose our tool, what we want to use. Okay, hence so this question, so it all started from this question, right? So the PXRD pattern is more spread out when we use copper radiation instead of molybdenum radiation, so this will be true. Okay, saved this, just save this. Okay, so we the next couple of questions was related to crystallization. So this crystallization is what? Crystallization is something by which when we have a compound, so we want to that compound may be amorphous or it may be microcrystalline. However, if we want to get large crystals, so what we usually do is we take the compound in a suitable solvent or mixture of solvent, and then we try out different methods. There are no hard and fast rule, but we can do slow evaporation, we can do fast evaporation, then solvent evaporation. Many techniques are there, and then we get crystals. So this process of crystallization, so the fourth question was that purity of solution affects the rate of crystallization. So this is obviously true, because if you have a compound and you have dissolved it in a solvent, and suppose you have to do in the lab, you have to do it in some vessel, right? You can use a conical, you can use a beaker, you can use a test tube. Sometimes even people do crystallization in NMR tubes also. However, so the vessel, suppose, which you are using is not very clean, it has residues of something which was previously there, then many things can happen. The previous residue can actually get into your solution which you are trying to crystallize and cause a kind of doping effect on the crystals which you are crystallizing. So it is very important to clean the glassware which you are using for crystallization, and in the process it is evident that the purity of solution is very important aspect of crystallization. So this is obviously true for this true and false question. Okay, then sorry, this will be true. Then this question, that crystallization can be used as a purification technique based on. So crystallization is a purification technique, but what is it actually based on? So it is so you have to see the options. So pressure, solubility, melting point and boiling point. Now when you are crystallizing, you are basically taking a compound in a solvent and then you are getting the crystal. So we do not usually vary the pressure, or we do not usually melt it or boil it or do anything of that sort. So crystallization is a purification technique which is based on difference in solubilities, right? So crystallization is actually a very good method to separate compounds based on their solubilities. So what is happening? So, suppose you have some compound, okay, some compound A, and then you have reacted it. So A can be, any molecule like this. I'm just speaking hypothetically, and then you have suppose used say formaldehyde, H HCHO. Okay, what does HCHO do? So HCHO, the structure is like this. Okay, so this is a carbonyl. Sorry, this is one hydrogen, this is one hydrogen. Okay, formaldehyde. So here this formaldehyde is a very good agent to cause this alkylation of CH2 methylene. Okay, so you can use a CH2 bridge here, and then here again you can use suppose you have used 2 moles of this A, where this part is your A, this part is your A, and you have bridged it using formaldehyde, okay, to get a structure like this, bridged compound, basically like A here and A here. Then what can you do? Obviously the first thing you can do is you can perform a column, okay, to separate, but you can also use the crystallization technique. How? So this A, so this bridged compound and your starting material, so your starting material is simply A, right? So these two will obviously have a difference in their solubilities in a particular solvent. Say for example Why? Because if suppose this is a polar molecule, then when you have bridged it, then what? Its polarity can increase or decrease, so depending upon how the bridging is occurring. And then the molecular weight is also different, right? So there will obviously be a difference in the solubility of the starting material and the product in any particular solvent. So if you now take the reaction mixture, okay, you take the reaction mixture, you quench the reaction, and then you dissolve that in that particular solvent. Then you, if you keep it for crystallization, then what will happen, it may be possible that this compound will preferentially crystallize out first. Why? Because this is having a greater molecular weight. Okay, and if you have completed the reaction, say for example like 24 hours or anything, you have completed the reaction, which means that the product is also in very much excess compared to the starting material. So the little bit starting material which is there will kind of remain in the solution, and the product will precipitate out as crystals, pure crystals, and you will get the pure product. So crystallization is very much useful as a purification technique, okay, which is based on the difference in the solubilities. So this is the correct answer. So then this was the next question. Which among the following affects the process of crystallization? So the options were slow cooling. Slow cooling will obviously affect the process of crystallization. Then this is very interesting, but foreign particles also affect the process of crystallization. So you may ask how. So the answer is, so in crystallization the first step is basically the nucleation step, and some foreign particles like dust or even a hair, a strand of hair, can initiate the nucleation process of crystallization. And humidity also affects. How can humidity affect? Suppose you are making crystals in the month of say December, which is very cool and the air is dry. I'm talking about our country. The weather is kind of dry compared to say the month of July, where it is the rainy season here and the air is very much humid, right? So when you are working in the lab, then you are supposed crystallizing a compound. You are trying to do that from say methanol or ethanol. So this methanol and ethanol, so until and unless you are using very dry solvents, okay, so there are techniques to dry the solvents in many labs. So until and unless you are using very much dry solvents and crystallizing in under this nitrogen glove box condition, so these solvents usually contain very little amounts of water in them, so you can't help it basically. And if the air is very humid, then the solvent can absorb more amount of water from the atmosphere, and then that water can also go into your crystals. Okay, so you might get a hydrate form, you never know. So all these factors actually affect the crystallization. So the answer will be all of the above. Okay, so the answer will be all of the above. Then the next question was that a crystal which is suitable for data collection, what are the requirements for a crystal which is suitable for data collection? So if a crystal has irregular shape, it is not a very good practice to use that for data collection. If a crystal has dimensions larger than the diameter of the X-ray beam, then obviously you cannot use that crystal for data collection, because you will not get the complete set of HKL reflections. Then if a crystal has a very high mosaicity means the domains I'm talking about, then it will not be able to fix the unit cell. Hence the answer here is none of the above. So this is the answer. Okay, then the was I think last question related to crystallization, that what are the factors by which crystallization is governed. So is it governed by thermodynamics only, kinetics only, both, or none? So the answer is that crystallization is governed by both thermodynamics and kinetics. If you look at the crystallization and if you think of it as a purely thermodynamic point of view, it will seem to violate the laws of thermodynamics, right? Because crystallization, what is it? It is a spontaneous process. Like, you don't have to pump energy into the system to get crystals or something. You just leave it and you get the crystals. It is kind of a spontaneous process. And what is the second law of thermodynamics? The second law of thermodynamics states that for any spontaneous process, the entropy should increase, right? But here, what are we forming? We are forming crystals. So what are crystals? Crystals are ordered structures. We are restoring order into the system. So entropy is decreasing, but it is still a spontaneous process, right? So then how is it happening? So if you think from this point of view, then crystallization, you cannot explain it on the basis of pure thermodynamics. Okay, you have kinetic factors as well. Hence crystallization is governed by both thermodynamic and kinetic factors. Okay, so then we will come to the next topic. So so why will we come to the next topic? Because the next set of questions, so these questions are about systematic absences, right? So before going to the question and answer solving part, so we will learn a little bit about systematic absences also. So basically, what are systematic absences? So if there is a set of lattice planes which occupy the lattice planes occupy such a position that when they are reflecting X-rays, then those X-rays are out of phase with another set of lattice planes, then no reflection will be observed. Okay, so for crystal diffraction, what do we follow? We follow Bragg's law, right? Now this systematic, as I said before, so Bragg's law is a very universal thing, and the presence of systematic absences also can be understood very easily and very, in a very clear-cut manner from Bragg's law also. So what happens is, so according to Bragg's law, all the lattice planes will reflect the X-rays, but if there is one set of lattice planes which are reflecting X-rays out of phase with another set of lattice planes, then the first set of lattice planes, we will not get the spots for that. Okay, so what is happening is they are reflecting X-rays, but means the Bragg condition is satisfied, but since it is out of phase, means there is destructive interference. Okay, so when this happens, when there are translational symmetry elements or centering in the crystal lattice, so this is very important. So what do you mean by centering in the lattice? So we have primitive unit cells, and then we have A-centered, B-centered, C-centered, we have phase-centered, and we have body-centered. So these centered lattices almost always have systematic absences. What does not have systematic absences? Primitive lattices, P. And then the second thing is translational symmetry elements. So what are translational symmetry elements? So you should know that by now. Screw axis and glide planes. So screw axis and glide planes contain translational symmetry components, right? So what is a glide? Glide means a mirror combined with some translation. Then what is a screw? Rotation combined with some translation. So when we have screw axis or glide planes, then also we get systematic absences. Okay, so the presence of translational symmetry elements or centering in the crystal lattice causes systematic absences. Then these systematic absences are actually very useful. So why is that? So because we actually determine the space group from the systematic absences by using our knowledge of systematic absences. Because certain symmetry elements cause these systematic absences, so it is how do we do that? We first search for the presence of symmetry elements in the following order. First for the unit cell, first for the centering, then for glide planes, then for screw axis. Okay, first we will look for centering, then glide planes, then screw axis. Thus, the careful tabulation of systematic absences in the X-ray diffraction pattern will allow the space group of the crystal to be assigned. Then after the determination of the unit cell dimensions is the next piece we need to obtain, and the space group determination is done systematically considering each class of Bragg reflections. Okay, like for example we have the H00, then 0K0, like that, and checking that this set of reflections in these classes, so either they are present or they are consistently absent. Okay, by that we assign screw axis or glide planes after assigning the unit cell centering. Okay, so let us try to understand the systematic absences from the Bragg's law, right? What is Bragg's law? Bragg's law means if we have a plane, so suppose this is a plane, this is one set of planes, so which are marked like this. So these planes, so let us assume that they are following the Bragg's law, right? And these planes, so if we index a unit cell, so this is actually forming a body centered sorry, is forming a body centered unit cell. So we have these atoms at the middle also, so these are the atoms at the centers. So these atoms are also forming a plane, right? So if this is this plane, okay, so we are visualizing it in 3D, but for simplicity then we are representing it as 2D. Okay, so this is suppose my A set of planes, right? Then here if we represent if it is like if we are suppose seeing it from this direction, so what is this direction? This is my A direction. Now if we see completely parallel to the A direction, we will simply see a line like this, right? And we will see these spots like this. So this is my A. And the center ones, so these are my B. Okay, this is my B. Now so this is like since this is the A axis, this is the BC plane, so we are considering this reflection, so that is not important. So what we will do is we will look at this beam 1. Okay, so beam 1 means this A set of planes. Okay, so 1 and 2, this and this, 1 and 2 are the same set of planes, the interplanar distance. So this interplanar distance, suppose this is D. These set of planes, A set of planes, they are following Bragg's law. They are undergoing the diffraction, and we will get the spots corresponding to them. Then what will be the Bragg's law? It is 2d sine theta is equal to n lambda, right? So this 2d sine theta is there. So this 2d sine theta is equal to some integral multiple of the wavelength which we are using, lambda, so that they will do this constructive interference and we will get the spots. Now let us consider the B set of planes. The B set of planes, like these planes. These planes. Here this distance is D, but like this D of 2, 2, 2 will be half of D111, right? Is half of that. It is something like that. So these set of planes, if we consider this distance, this is another set of planes, right? This is like suppose D prime. Now for these to undergo the Bragg's law, we will need 2 D prime sine theta is equal to some integral multiple in lambda, suppose. However, this d prime is what? This d prime is half of this d, right? So instead of d prime we can write d by 2. Instead of d prime, if we write d by 2, then these 2 and these 2 will cancel, right? These 2 and these 2 will cancel. Then what do we end up with? We are ending up with d sine theta is equal to some integral multiple of wavelength. So this is not the Bragg's law. So the Bragg's law is not satisfied. Hence, the set of reflections from this B set of planes, that is the rays from 3. So this is 3, which is falling on the B set of planes, will be, thus the rays of from 3 will be exactly out of phase with those of 2. That is my A set of planes, and no reflection will be observed from the B set of planes. Thus, we are having systematic absences. Why we are having systematic absence? Because this is a body-centered cubic lattice. In other words, there is a centering, right? So this is simply the systematic absences. So so this is all about systematic absences, and as I said before here, so in addition to centering, the translational symmetry elements like screw axis and glide planes will also cause these systematic absences. And to understand more about it, so you have to go to the lectures of week 5, and you can go through the lectures again, and then I'm sure you will understand all the details about the systematic absences from the screw axis and the glide planes. Okay. So now we come to the questions. Okay, the assignment questions. So the first question related to systematic absences was that systematic absences in the X-ray diffraction pattern will allow the space group of the crystal to be assigned. So which is true, because when we take the X-ray diffraction pattern, you have learned, right? So from the concept of reciprocal lattice and evolved sphere, that the no matter the crystal structure is centrosymmetric or non-centrosymmetric, the diffraction space is always centrosymmetric. It will belong to one of the Laue groups. So using only that much information, we cannot actually assign the space group. We need the systematic absences in order to systematically look for the present reflections, and then from there we deduce that whether a screw axis is present, which centering is present, glide planes present or not, and then we step by step we assign the space group of the crystal. So this is true. So this is true. Then Bragg's condition is not satisfied for the reflections undergoing systematic extinction. So you have so this is so as you can see here, okay, sorry, so where were we? Okay, so which of the following reflections will be absent for a BCC lattice? So the explanation which we gave for systematic absence, so we considered a body centered lattice, right? So for body centered lattice, so the condition is that the sum of H plus K plus L, if it is odd, then those reflections will be systematically absent. So the absent reflections will be H plus K plus L is equal to some odd value of integer. So here the options which were given, so if we go from top to bottom, so we have, so this 1 plus 1 plus 1 means we have 3, we have 2, we have 2 plus 2 plus 2 means we have 6, then 1 plus 2, 3 plus 3 means we have 6. So here only this is odd, right? Hence this 1 1 1 reflection. So for a body centered lattice, this 1 1 1 set of reflections will be systematically absent. Okay. Then the next question was the orthorhombic space group PNMA will have systematic absences due to. So what did we learn? We learned that systematic absences can be due to lattice centering and due to screw axis and glide planes, right? Center of inversion is actually not a condition to cause systematic abscess, so this is gone first. Then what is there? It is lattice centering, but this is a primitive unit cell, right? Hence this second option will also not be true. The first option is not true. This is P primitive. The second option is also not true. We have screw axis. PNMA means what? So all these three are mirror and glides. Hence there are no screw axis in this space group. Hence this has to be the correct option. Because there are glide planes, so these glide planes are responsible for systematic absences in this orthorhombic space group PNMA. Okay, and that is all. Okay, sorry, we left this question. So Bragg's condition is not satisfied for the reflections undergoing systematic extinction. So what are systematic extinctions? So extinctions are nothing but the systematic absences. Okay. So what we are seeing, these systematic absences are also called as extinctions. Okay, and the presence of these systematic absences can be understood in a simple way from Bragg's law. Right, this Bragg condition is satisfied for the set of planes in question. However, there is some destructive interference which is extinguishing the reflection. Right, hence this is actually false. So this is false, because we are getting the destructive interference, right? So this is false. I think we have covered all the questions. Let me just check once. Yes, so we have covered all the questions, and so additionally, if you have any questions, so just post it in this, you can post in the ask a question tab. Okay, so see you all next week. So thank you.